When I was teaching in public school, I would drive my car up and down the street that was adjacent to the school with my hand pressed on the car's horn. Now, students would be standing by the back gate and they would listen to the sound of the horn as the car approached them and the sound of the horn as the car moved away. And they noticed that the quality of the sound changed. The pitch of the horn was higher as the car came towards them, and then it fell off as the car receded. You might have seen the same thing if you were standing at a train station and the train approached the platform blowing its whistle and then sped past the platform. You would have noticed that the pitch of the whistle changed. The pitch got higher as the train approached, and then it fell off as the train receded. Now we know that sound travels as waves, so something is happening to the sound waves as the train moves towards the person that is standing on the platform. Now, how does this happen? Now, an interesting thing to keep in mind is that even though the pitch of the sound changes, to me, sitting inside the car, the horn sounds the same all the time. I notice no difference. And the same thing applies to the driver of the train. When he blows the whistle, even when the train is moving, he does not notice any change in the pitch of the whistle. So the change in the pitch is an apparent thing. It's not a real change. It is a perceived change based simply on the motion of the object that is emitting the sound. So how does this happen? Imagine I was throwing some tennis balls and you were catching them, and let's say we are standing at opposite ends of the room, and I am throwing the tennis balls one every second. Now that is my frequency. The frequency at which I'm throwing the tennis balls is 1 per second. Now as long as I'm not moving and you're not moving, the tennis balls will get to you 1 every second. Now what if I start moving towards you? I'm still throwing the tennis balls 1 every second, but you will perceive that the frequency has changed because the tennis balls will get to you faster and faster, because as I'm moving towards you, the balls have less distance to travel. So you think that the frequency has changed, and you're telling me, Mr. Sub, you're throwing the balls faster. But no, I'm throwing them at the same pace. It is just that I've started moving towards you. So in other words, as I move towards you, the frequency changes, the frequency increases, and if you were to plot it as a wave, then the frequency would increase and the wavelength would decrease. So these are more crowded waves. So as the train approaches a platform, the waves are more compressed. They are packed more tightly, so the frequency is higher, the wavelength is smaller. So this apparent change in frequency of a wave is called the Doppler effect. Now we know that light also travels as waves, so obviously the same effect will happen if we consider light waves. So if an object is moving towards you, then the light waves would become, apparently, would become more compressed. The frequency will increase, the wavelength will decrease. So in other words, to the observer, the light would appear more blue. But if the object was moving away, a source of light was moving away, then the frequency would become less the wavelength would become larger and the light would appear more red. So, when scientists study objects in space, stars and galaxies, and they study the light that is coming from these objects using spectroscopy, they notice that the characteristic lines in the spectrum that belongs to hydrogen and helium. And why do I say hydrogen and helium? Because the stars are composed of hydrogen and helium. So when you study the light coming from the stars and galaxies, you are looking at the signature pattern of the lines in the spectrum that hydrogen and helium make. Now, when scientists study this spectrum, they notice that these lines are shifted towards the red end of the spectrum, which means the star is moving away from us or the galaxy is moving away from us. And in all the light they have analyzed of all the stars and galaxies, all the shift is towards the red end, meaning everything in the universe is moving away from us and away from each other. So if everything is moving away from each other and from us, then it stands to reason that at some time they must have all been closer together in one place. And then the question is, so if you walk it backwards, then all the stars and galaxies must have been in one place at one time. Then the question is, what got them moving outwards? And scientists theorize, or astronomers theorize, that there must have been a Big Bang that started everything scattered out in space. And that is how we get to the Big Bang theory. So it is all tied to the Doppler effect, which is the apparent change in frequency of a wave because the object that is emitting the waves is either moving away from the observer or moving towards the observer. And the Doppler effect applies to a train whistle just as much as it applies to the Big Bang theory.